Hello, all, and welcome to our new topic as we start to look at exponentials and logarithms. That's the breakdown of the topics that we'll be working through. 5A is general exponential functions, and then 5B is we'll look at the exponential function, which will make a little bit more sense when we look at it. 5C, we're solving exponential equations, and to help solve them, we need to then use logarithms. So that's what we look at for 5D, and then graphing them in 5E. Determining rules for graphs, so similar to what we've done for quadratics, cubics, quartics, for everything, is what patterns are we recognizing? How can we use those patterns to find an equation given certain key information and do that efficiently and quickly? 5G, solutions to exponential using logs, and then a bit of a look in inverse, and then exponential growth and decay. So that's what we're going to work through for this topic. So let's get straight into it. What is an exponential function? Well, so far, pretty much everything we've looked at has been effectively some form of a polynomial or very close to a polynomial, where our variable or a function of our variable x, we have some power to it, x to the n, where n has been natural numbers, mainly integers. Technically, they could have also been fractions when we were doing things like that, and 1 on x squared. But they could all be brought back to some written in some form like that. What we're changing now, instead of our variable being the base, x, we're actually making that the power. Okay? So we have our two basic ones that we're going to look at. F of x is equal to a to the power of x, and then f of x is equal to a to the power of negative x. So let's have a think about that relationship between coordinate pairs, just to get an idea of why this shape is like it is. If we pick any number, let's, for example, f of x is going to be, and this a, the base, most of the time, that's just a number, picking some number. A lot of the times we're going to be just picking 2, 3, 4, some more simple ones to work with. But let's say it's just 2 to the power of x. Okay, so let's do a bit of a table and think about what happens as we make x larger. What's going to happen to the y coordinate, or what's going to happen to our function? Well, if I put 1 in, 2 to the power of 1 is just 2. Then if I put 2 in for the power, 2 to the power of 2, that's 4. 2, now I'm putting in 3, so 2 to the power of 3 is 8. 2 to the power of 4, we get 16. 2 to the power of 5, we get 32. So what do we notice? Well, this time it's gone up. If we think of addition, up 2, we've gone up 4, we've gone up 8, we've gone up 16, or it's multiplied by 2 every time. It's growing really quickly. Our y value gets really big really quickly just from a small increase in our x value. So straight away, if we have x is equal to 7, we already get our y value is already 128. It grows really, really quickly, and that's where you might hear things, exponential this, exponential that. It's referring to something that grows really, really quickly, especially when you think of exponential growth. It's something that takes off all of a sudden. A great case study has been COVID cases, that when they first hit, it starts really small and then it ramps up really quickly as it spreads. That's an exponential growth. And that can be modeled through exponential growth. But that's a quick look at it. Same thing goes for as we make x smaller and as we move x into negative numbers, that will make our function really, really, really small. A thing to note is, can we ever get y equal to 0? So let's think of our case, 2 to the power x. Can I put any number in there that gives me a y of 0? Well, the first thought you may have is, just stick 0 in there. Well, 2 to the 0, anything to the power of 0 is equal to 1. Doesn't matter what our base is, if it's power of 0, it's actually equal to 1. And then even as we put negative numbers in there, doesn't matter how big a negative number, we still can't get y equal to 0. So what we're getting, there is actually an asymptote here at y equals 0 that we need to be aware of. And that's a really good thing to know, because when we start looking at translations, we can start using that as our reference point. So there is an asymptote at y equals 0. This first graph, this is our sort of basic one. More common one is when our base is positive, greater than 1. So this we would consider, this is our most basic shape. When a is greater than 1, this is our most basic shape, and it's going to go through 0, 1, because it doesn't matter what base you choose. When you stick 0 in the power, it turns it into 1. When we put 1 for x, we're always going to get our base, and when we put negative 1 in, we're going to get 1 on whatever our base number is. So to show this sort of pattern, I could do f of x is equal to 4 to the power of x. Well, that's going to be a 4, and that's going to be a 4 there. Okay? At negative 1 and 1. For the most basic form before we start translating. Same if I said this was 15. Well, that's going to be 15, and that's going to be 1 on 15 there. But it's always going to go through 0, 1 for the most basic form before we start doing transformations to it. The other one to be aware of, and this down here represents how they are very similar, is what happens if our base is a fraction between 0 and 1, or a decimal between 0 and 1. So a great example would be 0.5 to the x. Well, we can actually write that 0.5 if we look down here. Okay, we can write that as half, and then using our index laws, well, we can actually write that as 2 to the power of negative 1. So then we can again use our index laws, and we can actually write that as 2 to the negative x. So in this case, if we have 1 on any number to the power of x, we can actually rewrite that as that number to the power of negative x. So we can work it like that. And if we think about it, if we go from a function that is a to the power of x and we change it to negative x, if we think of our rules still hold for all our transformations, shock horror, what happens if I take my x and replace it with a negative x? Well, we know that it is making the graph reflect about the y-axis. It's making all our x values switch their signs, so we're just flipping it about our y-axis. All these values over here get flipped over this way, and all the values over here get flipped over here, and we have the same graph just reflected about the y-axis. So that's our two basic forms, but as long as we can even work with this one here on the left, and then think through our transformations, we can always get to the final product. It's just really handy to think, if we've got a decimal less than 1, how can we rewrite that so that it's actually a number greater than 1? And that'll make it easier to identify transformation. But that is already 8 minutes in, so a lot of talking. So let's fly through these translations. Now you can pause these and work through. Every one of these slides has the full dash method explanation, where that first step, which is the same for inspection or dash method, is write as an equation that has every operation applied directly to a x or y. Write as an equation where every operation is applied directly to x or y. Okay, so for example, if we have y equals 2x minus 1, well, the 2's are, this 2 here is our base, so that's fine, that stays there. This minus 1 is applied directly to the x, so that's also fine, so fine. But this plus 2, that's not applied directly to the x, so how can we rewrite this where it's applied directly to something? We bring it over here to the y, so we can write it as this bit here. Now that we've gone to that bit there, You can do the dash method, which is all of this, or we can use our inspection really quickly, where we can see the most basic form has to be y equals 2x, y equals 2 to the power of x, sorry. What are our transformations? Well, or what are using inspection? I've replaced x with x minus 1, and I've also replaced y with y minus 2. So straight away I can see this is a horizontal translation plus 1 to the in the positive x-axis, and I can also see this is a vertical translation plus 2 in the y-axis. Ran out of space, but that same method applies. If we rewrite the equation where every operation is applied either directly to the x or the y, and then if we use your inspection method, you can read them off just like everything we've done. So thinking of that, what would be our base graph? Well, our base graph is y equals 2 to the power of x, which has an asymptote at y equals 0. It's going to come through. It's always going to go through 0, 1, the base version of it. 1, whatever my base is, so 2, and over here, that would be -1, 1 on 2. So that's my very most basic form. That's why it's really important to learn this pattern of these 3 coordinates, because if you can know those, and then every transformation, you can just apply it to it. So we know then that base form is translated 1 plus 1 this way, and then plus 2 up, and that's what it looks like there. You can see the asymptote has been moved up 2, and all the coordinates have been moved across 1 as well. So that's really handy. So that was translation, sorry. Now let's look a bit at reflections, and the first one, which we've already really briefly looked at, is if we have a reflection through the y-axis. So we're reflecting about that y-axis there. We're starting with a graph of y equals 6 to the negative x. Is every operation applied directly to the x or the y? Well, the 6 is our base, so that's fine. The negative sign is applied directly to the x, and that's it. So yeah, they're both written as. So I can read those, thinking of what would be my most basic form. Well, it has to be y equals 6 to the x. What have I done? Well, I've replaced x with negative x. I can read that off straight away, or you can use the dash method as shown there. What do we know if x has been replaced with negative x? Well, that is reflect in the y-axis, or about the y-axis. So the basic format, y equals 6x, would come through like that, goes through 0, 1, it would go through -1, 1 on 6, and we can see that all the coordinates have just been flipped. That's been flipped over there, and this one, which would be at 1, 6, has been flipped over that way. So again, we can look at it through inspection. What if we have a negative out the front in this case? Well, that negative isn't applied directly to the x, so we want to rewrite that. So we can now rewrite that as what negative y equals 3 to the power of x. 3 is our base, so that's fine. The negative sign is applied directly to the y, that's fine. So that's everything that's happened. So what would be our basic version of the equation? Y equals 3 to the power of x, which would go through 0, 1, go through 1, 3, and it would go through -1, 1 on 3. Now, the y has been replaced with the negative y, so y placed with negative y. Sorry, I'm still a bit sick, so I'm still a bit croaky. Y replaced with negative y, so we are clearly reflecting about the x-axis. Every y-coordinate has been, its sign has been changed. So it's flipped down, it's flipped down, it's flipped down. So again, if you know the base, what that base is going to look like, and it's also going to have 3 key points, that's really handy. Lastly is applying a dilation factor. Okay. Now, how do we apply a dilation factor when we've already got a number in the base? Well, is by multiplying by some number out the front, and we generally call that k in this case. So, how does this work out? Well, same thing. You want to write it where everything's applied directly to the x or directly to the k. Directly to the y. So the 8 is our base, so that's fine. A 0.2 is definitely not applied directly to the x. And we can see here 0.2 is the same as 1/5. That's a really handy thing to recognize. So we could write it as 1/5. Divide the right hand side by 1/5, divide the left hand side by 1/5 as well, and we get this situation where y is divided by 1/5. Now, how do we do a division by a fraction? Well, that's the same as multiplying by the fraction flipped. So that's going to be like that. And so we can get 5y is equal to 8 to the power of x. So that is now written in a form that everything's being applied directly to the x or directly to the y. Trying to read the replacement, we have replaced y with 5y. And this is that tricky one. When we do dilations, you need to remember that we're normally reading the dilation when it's divided by. So say if we replaced y with y on whatever number is b, in this case it's technically, we could have left it like this form over here. Sorry, I'm going a bit quick because I'm cognizant of everyone's time. But this y divided by 1 on 5, well, we can write that as y divided by 1 on 5. And we can read that's clearly our b, our dilation. Because our dilation is always written underneath when we look at it in terms of replacement. So we can see we have dilated by a factor of 1/5. And again, like I said, you can pause the slides, have a look through the dash method. It's on all these slides. But using inspection, we can see dilated by a factor of 1/5. Okay. And what coordinate are we changing? Well, we're changing our y coordinate. So to change the y coordinates, okay, we're taking some y coordinates and we're stretching them. Okay, that means we're actually dilating from the x-axis. And this is why we spent so much time doing the transformations, because it's going to come up in pretty much everywhere. So that's dilating from the x-axis, and of course you can have a dilation from the y-axis. So in this example, we're given y equals 9 to the power of x on 2. Well, is that written in a form where every operator is applied directly to the x or the y? Well, 9's our base, so that's fine. This is x divided by 2, so that's fine. So we can see straight away the most basic form of that graph would be y equals 9 on x, and we have just replaced x with x on 2. So we can quite clearly see our dilation factor is the 2. So we have dilated by a factor of 2 from the... Now, if we're changing the x-coordinates, that means if I again draw this graph in the most basic form, like that, where that is at 1,9. This would be at negative 1,1 That's the basic form here. Okay. All of those x coordinates are being stretched away. Okay. So what is that? We're actually dilating by a factor of 2 from the y-axis. Okay. Technically, it's being stretched away from the y-axis. So that's a quick look through all the transformations. Again, I know I've gone through them really quickly. Pause the slides as you need be, and think of, go all the way back to this, think of these 3 key points. They occur at x equals -1, at x equals 0, and x equals 1. And if you can think of those 3 and then think, okay, once you've identified what your transformations are, either through the dash method or through inspection, just think, okay, what's going to happen to those 3 points? They're going to be stretched or moved up or down, moved left and right. Great way to work through the problem. So, following on from that is when sketching exponentials, it's important to identify the shape first. So once you've identified, especially the reflections, it's important to think, is it reflecting about the x-axis? Is it reflecting about the y-axis? Because once you do know that, and then if it is translated up or down, you might know where the intercepts are going to be. Okay? So think, what is the rough shape? Which way is it going to be? Is it going to be the most basic form that goes up like that? Or is it being reflected about the x-axis? It goes down like that? Or is it being reflected about the y-axis? Or has it been reflected about both axes and goes like that? That's our 4 main shapes. Once you've got that, and then thinking of any vertical translations, okay, put in your asymptote. And then once you've got that, you know, okay, I'm going to have an intercept there. Get that. Once you get that, get one other point of reference. Generally, it's really nice to do either x equals 1 or x equals -1. Going to make your math a lot easier. And yeah, sketch the curve. So that's your steps, suggested steps to work through. As it says down here, if there's no axis intercepts, then at least 1 point of reference is required on the sketch. I still really like, even if there is one intercept, put in a second point so it has some sense of scale to the shape. At the moment, because I haven't gone through it, we haven't done logarithms this year, so there's no requirement for you to use logs yet to solve anything. So when you use logs is when you're given, you might be said, f of x is equal to 1.0004 to the x. Find x when f of x is equal to 1.1 in this case, which gives us this equation. Well, how do we get the x by itself? What's the algebra that we do to do that? Well, it's logarithms, but we haven't done it yet. So at the moment, just use the solve function on your CAS. If there's for some reason you need to do that, or you're trying to figure out an intercept, that's where this will probably come up when you're trying to find the x value. So you're probably trying to find an intercept. Just use solve, and that's a really good thing to do anyway, because you want to get efficient at it for exam 2. That's it, 23 minutes. I apologize going a little over time. But yeah, all the best for exercise 5A. If you have any questions, don't hesitate to comment below or email me or put something on Google Classroom. Don't be afraid to also go look at the textbook. Great reference and worked examples in there as well. Have a good evening.